class. Hope you guys had a good lunch.
No, it's good.
But today we'll be talking about X-ray interactions with matter and micro-level interactions. We're doing chapter 7, okay?
Do you know my English?
We'll do
No,
four.
I'm gonna mess with
Make
it.
sure you write down everything.
That was a good idea. Because I noticed it too.
So
I
the
noticed it
overview,
too, so it's a good
I
idea.
like that type of teacher.
I apologize. I'll bring the stickers next time. But the
As long as I
overview,
get a gold one.
I got you, sparkling. But the overview that we'll be talking about today is the different types of photo interactions. There's 5 interactions that Mr. Phung has said. So there's classical scattering, photoelectric absorption, Compton scattering, pair production, and photo disintegration, okay? And there's types of different absorption. There's transmission and absorption, and then there's different types of micro level interaction. Maintain scission, cross linking, and point lesion. So before we start getting into the whole sense of PRE, right? We have to know cause and effect. So this is how I like to compare interactions, right? So there's a quote that the law of cause and effect states that every cause has an effect, and every effect becomes the cause of something else. Okay. For example, if I went up and I smacked the computer down, right, it should beat me up, right? So the cause is what? I'll slap the computer down. It's a big computer.
Don't be mad.
If I smack the computer, that's the cause, and the effect is that she's gonna get mad at me, right? So the same thing with X-ray interactions, correct? So the cause is we're shooting these X-rays, right? We're creating these X-rays in these tubes, which shoots out an X-ray photon. And where does that photon go? Onto the next slide. So as you can see, it goes to the matter. So I have a little key symbol right here. So the X-ray photon is being shot. It's the X-ray photon, and it interacts with matter right here, correct? So purple. And when I say matter, it's the human body, preferably, correct? So purple matter. So as you can see, X-ray photon hits the matter, and it creates an interaction. And this is the effect that causes, right? So what was the cause?
The machinery.
The machine, we're causing X-ray photons, we're producing X-ray photons, and what is the effect?
Like photons.
The photon interacting with matter, encased the human body, correct? Yes, sir?
So in this sense, X-ray photon is synonymous with the filament electron? Or is it?
So what do you think, Jalen? Is the X-ray photon the same as the filament electron?
No, because the filament electron is what happens after the interaction occurs. No? Or is it the same?
All right, so let's think about it. Where does the filament electron come from?
From the
filament.
cathode.
Right, from the filament at the cathode end of the tube. Great. Where does the filament electron go?
To the anode.
Right, to the target, to the anode. Okay, when it reaches the target at the anode, what three things could happen to that filament electron?
It can be filtered out, or it can be a photon.
Transmission,
Okay.
absorption,
So
transmission.
remember, we're talking about interactions at the target. In
Oh,
other
okay,
words,
I
what
understand.
you just discussed last week.
Primary, right.
So characteristic,
And Brahms.
grams,
Oh.
and
Heat.
heat. Very good, right? Those are the 3 things that could happen. The electron hits the target and it either produces heat, grams, or a characteristic. So, heat is heat, right? But characteristic and Brem's, what do those 2 interactions produce? X-ray photons. So are those photons the same as the filament electron?
No.
No, right? The filament electron was the cause, and the effect was the creation of
X-ray photons.
X-ray photons. What are some differences between a photon and an electron?
Main is that
Okay, so Shaheen,
electron is negatively charged, photon is positively charged.
electron is negatively charged, photon has no
Or no
charge.
charge.
Just energy.
What is
X-ray
not a
photons have no
photon?
charge. All right, so Jay, do you have another difference?
I was just gonna say it's levels of energy.
Levels of energy?
Like the photon itself is a packet of
So
energy,
one side
whereas
come
an
off with a
electron
reason, the
is
other one
charged
didn't. I wonder
with
why.
energy.
Okay, great. All right, so second difference between an electron and a photon. An electron is matter. An electron is matter. It has mass. It is a physical object. Okay, an electron is matter. Are we comfortable with what matter is? Right, a physical object. It's really tiny, right? You can't really like touch it, but it's a physical object that has a charge. A photon is pure energy. It is not matter. It has no mass. It has no weight. It cannot be affected by things like a gravitation. Well, actually, that's debatable. But it can be affected by like a magnetic field, the same way an electron can. Right? So electrons are matter. Photons are energy, pure energy. Okay, so that's a second big difference between them.
That's a test question right there.
Thank you. Sorry, Jalen.
Thanks. Sorry for what?
For
Alright.
taking that time.
I know it's good. You got questions? If anyone has questions, don't be afraid to ask. Okay?
So let me ask, what comes out of the tube? Does the electron leave the tube or does the photon leave the tube?
Photon.
Great, photons leave the tube. So will electrons leave the tube and interact with your patient? No. What leaves the tube and interacts with your patients? Photons. So during this presentation, as Jalen presents these interactions, the incoming object, the thing that is coming and interacting with the matter, what is that thing going to be?
Photon.
That's right, it's the photon. So it is going to be our incident photon, right? In Brem's and characteristic, we had an incident electron, the incoming electron. But here, for the rest of this chapter, we are only going to be talking about an incident photon, because only photons will interact with the body, correct?
Yes, sir.
Yes.
We're good? We're clear? Yes, Reagan.
Can you just wait one more time? Sorry. Can you describe the incident photon for me?
A photon is a packet of pure energy with no mass, no weight, and no charge.
Like the incident one.
Oh, incident just means it's the incoming one.
Okay.
So for all of these interactions, something is going to come in and interact. The incoming item is going to be your photon. You will never have an electron come in to interact with the body. Right? Because only photons leave the X-ray tube.
Oh, yeah, you just answered what I was supposed to ask. Okay.
So are we all on the same page here? All right, great. Take it away, Jay.
I have a question. So where does Bremsstrahlung and characteristic, where does that occur? Does that occur outside the tube or in the tube? Inside the tube, okay. And then what we're talking about, that happens when we have interactions with the body, okay? Just to clear that up for you guys. You had a question? You good?
So now this is outside.
Outside the tube.
So that's what we talked about.
Red circle is the atom that is inside, right?
Yeah, it's just showing where
This
the
is where the atom
interaction
is
is
being,
occurring.
the interaction is
So we're
occurring.
talking about the primary.
So then
Now this is inside the atom, like when we say the electron comes inside, the electron is coming in and is dividing.
The photon. The photon's interacting.
So the one that is coming, oh, this is,
This is
This
outside.
is outside the tube, like what's coming out the tube. That's
and
what
what
we're
the
talking about.
circle is circle.
Inside
Oh, the
the
circle
body.
is just to identify where the
Yeah, he's
interaction
just
is
showing you
happening.
what happens when the.
When the,
Yeah,
this
when
is
the
probably the
photon-
circle, a circle is where the patient is.
No. The circle is just to show where the photon and the matter is hitting. So here's the photon. It gets shot in by the X-ray, and it interacts with a matter, a piece of matter right here.
And the matter is the patient at the
Yeah,
that part, right?
for the most part, yeah, human body.
I see.
It's occurring in the human body.
Okay.
Everybody's clear?
Mm-hmm.
On to the next. So before we get to know everything about the human, we have to know how the atom works, right? So what makes up the atom inside?
Nucleus is inside.
It's the nucleus and the proton. And does the neutron, does it have a charge?
No charge.
No charge. And does the proton have a charge?
Yes.
Positive. Awesome. And then over here we have these rings. Electrons, correct. And then which one will have the strongest binding energy towards the closest? Okay. And then do we know the lettering system as well?
Yes.
Okay, sure. Perfect, perfect. And where's the valence electron located? Valence
The
electron.
outermost, right?
Outermost.
This is a test question. So the valence electron is the most outer electron on the orbital ring. So it will be number 1 because it's the outmost electron ring. So that would be considered a valence electron.
I have a question for you.
Yes, ma'am.
Why do you have the alphabets and of the rings in a on jumbled up?
So it's
Doesn't it go in a sequence?
excuse me.
Doesn't it go in a sequence? The
It comes in
names?
sequence. Yeah. So
But you have M before N and
it was last minute. My apologies.
so it has to be in a sequence,
Yeah,
right?
sequence should be in sequence. Yes, ma'am. Good eye, good eye, very good eye. So we basically went over this. So we're going to the next one. And so there are 5 different types of interactions that can occur.
So what does balance mean?
Valence.
Valence.
The valence, a valence electron is the most outer electron shell.
Then what does valence mean? Does the word have a meaning besides the fact that it's the most outer
No, that's just
That's a great question. Let me look it up for you while you continue. Kate.
yeah. Valence is just known for like the most outer.
Is it in the text?
Valence shells is the last outermost shell.
Is the inner shell called something?
So what about the inner shell?
Is it called something?
Oh no, it's just in the inner shell. Yeah, inner shell, and that has the highest binding to the nucleus. So from this occurrence, there can be 5 different types of effects that can happen. So the main 3 common ones is Compton, classical, and photoelectric. This is all found in diagnostic imaging. Okay, Compton, classical, and photoelectric. And this is measured in KeVs, kilo electrovolts. Okay. And the other 2, these are very uncommon for what we see. This is not found in diagnostic imaging. Per production, photo disintegration. And this is measured in MEVs, mega electron volts, okay? Very important. This can show up in your test.
By the way, to answer your question, Charo, no, valence has no other definition other than the measure of the outer electrons available.
VALENCE, right?
Correct, valence.
The combining power of an element, especially as measured by the number of hydrogen atoms it can displace or combine with carbon.
Mhm.
With carbon always has a balance, number of 4.
So valence, so in that case, is still talking about the number of electrons. That definition is confusing. The definition is confusing, so just think of your valence as the number of outer electrons.
Everybody good on this?
It's fun.
By the way, guys, if you are gonna take notes, I recommend taking notes on things that are not in your book. Right? There's no point just recopying your book a second time. So pay attention to what's up here. Think about what you saw in your book when you were doing your flashcards, and make notes of either highlighted, underlined stuff, or stuff that you don't remember seeing in your book.
You sir?
What's the other name for classical?
Classical. We're gonna go into it.
Coherent?
Coherent. We all good? Okay. Going to the next slide. So the first one we're gonna be doing is classical scattering. So classical scattering, the main significance about this, it affects the outer electron shell, so the valence electron shell, most likely. But since it only occurs between lesser than 10 keVs, it's a very small amount of energy. So what it would do, it would excite the electron shell and just shoot an opposite direction, but with the same energy. If there was a GIF right here, so the X-ray photon would come interact with the outer shell, excite it, and shoot it at a different angle, but it had the same energy. And these are the other types of names right here. So what I kind of remember classical, think of classical singing, they sing, so your vocal cords are vibrating, so it vibrates the outermost electron shell. And then you can do coherent, elastic, unmodified. Like unmodified, you don't want to modify your voice, right? You want to have natural. And then Thomason is a very old name, like Thomas, Thomason. It's an old name, so classical. That's the way I remember these names most. But since these electrons, these photons are very low, these are most likely being filtered, okay? And what happens to the beam when it's filtered, does anyone know? This is a previous, go ahead.
It hardens.
It hardens, okay. And so does that increase the quality or the quantity?
It increases the quality
Quality?
by reducing the quantity.
Say that one more time.
It increases the quality
Okay.
or the average quality by reducing the quantity.
Alright, perfect,
By
excellent.
reducing the quantity of what specifically?
Low energy photons.
Great.
Mhm.
Right, so classical, right? Classical scattering requires low energy photons. Filtration removes low energy photons. So that's why you don't see much classical scattering normally in diagnostic, because the filtration has removed most of those low energy photons. Now remember, filtration never removes all, right? It only removes a percentage, right? But it removes most of your low energy photons. So, let's see, Carla, if I have a 5 keV photon come in and it interacts with an atom through classical scattering, what energy will my scattered photon have? So incident photon comes in with 5 keV of energy, and then it interacts with classical scattering, and then when it comes out as a scattered photon, how much energy does it have? It still is going to be 5. Very good. Will it have the same direction? Is it still going to travel in the same direction? No, it will not. It will change direction. Very good.
Those two are the key factors of what classical is. It doesn't lose any energy, and it also has a different angulation from interacting with the atom. So definitely write that down. That'll be on your test. Is everybody done writing this down? We good to go?
You said doesn't lose energy or what?
It
Changes
changes directions. And it occurs less than 10 keVs, okay?
It does change direction or it doesn't change direction?
It does change direction. The one from above.
Yep.
The voice in my head.
The voice on my. Are we all good? Any questions on this? No, so on to the next. So coherent is the same thing, just a different name as classical, okay? So yeah, we went over this. So the key factor is that when the X-ray photon interacts with the most outer, what's the most outer ring called? Valence electron. It would excite it, but it doesn't get knocked out. It only excites it, and it shoots another electron with how much energy? Same energy. At what direction? Same or different direction? Change the direction. Perfect. And this is basically this entire slide is talking about. So yeah, just remember that key factor of this occurrence right here.
So it shoots off, you said it shoots off another electron, or does it shoot off another photon?
That's the following question. It's your question.
Right? So, what do you think, Jaden?
It shoots at a secondary incident photon.
Photon, very good. Photon comes in, photon comes out. The incoming photon, your incident, and your outgoing photon, your scatter, same energy, different direction.
And then just remember the names of the two. So incident, think of like the first incident, it's the first occurring one, and then secondary photon is the secondary one that comes out.
Is there a tertiary?
Tertiary?
Like
No.
No?
So what is all this talk about electrons in this slide?
All right, so, or do you want to take this one, Jaden? So, this is basically what happens. You've got your atom right here. Okay, in comes some energy. All right, energy comes in, hits the electron. What is connecting the electron to the atom? What connects the electron to the atom? Think about it. What did we talk about last chapter that connects an electron to the atom? What is that attraction? What? Again? It is the binding energy,
Good job.
right? So the electrons have binding energy, right? They're being held to the atom based on their binding energy. Now, let's say you've got this photon that's coming in, hits the electron, and the photon has less energy than the binding energy. What will happen to the electron? Does it get kicked out or does it stay? It has less than the binding energy. So it stays, right? Like we said when we were talking about characteristic interactions, you need more than the binding energy to kick out an electron. If you have less, then the electron stays, right? But the electron still just gained a whole bunch of energy, right? So energy comes in, electron absorbs it, it doesn't get kicked out, but it just got a whole bunch of energy. So now it is vibrating, it's super high energy, right? It's excited. And then it's like, all right, I'm done being excited, I'm gonna calm down now. And then it relaxes. It drops back down to its normal relaxed state. But in order to relax, what needs to happen to this energy?
To give away the
Right, it has to get rid of the energy again, right? So, in order to relax, the electron gives off energy. How much energy does it give off?
difference between the two.
The same amount it absorbed, right? It absorbed energy, got excited, it gives off the same amount to relax. When it gives off that energy though, it can give off that energy in any direction. So that's why photon comes in, excites the electron relaxes, photon comes out, but in a different direction. Same energy, but different direction. So the electron here is just kind of like the intermediary, right? It's that in-between step. It's the thing that absorbed the energy and then got rid of the energy again.
Okay, so coming in photon, electron, coming off photon.
Correct. Right? It's kind of like in a baseball, right? Right? Because we've got like the Astros playing tomorrow or something, I think. Right? So, right? Outfielder, right? Trying to get the person on the bases out, but they gotta throw pretty far, right? So instead they like throw to one person catches it, throws it to the next person, right? So same baseball, right? Same energy, but the direction ends up changing halfway through, right? Because it hits that middle person, right? So same thing, right? Photon comes in, hits the electron, this is our middle person, right? And then when they throw it off, it goes in a different direction. Same energy, different direction. Right? Or like in basketball or in soccer, right? Just anytime you like pass the ball around, right? Same energy, but it changes direction.
But it's still photon, right?
What does that mean?
It's still photon, right?
Still photons, yes. It's not like you throw the baseball and then the other guy throws out the basketball. Right? Same photon, right? It's still a photon.
Perfect. Good explanation. And then, yeah, so the same thing that we talked about. So, for example, what would be the cause of this interaction? Like, how much energy would you need to perform this interaction?
Less than 10.
More than
Less-
what?
Less than. Go ahead.
Less than 10 kilo electron volts.
Okay. And then, where in the orbital shell is it affected? Outer shell. Okay. And then, what effects happens after that? Scatters. And then, what does it do to the initial electron? It excites it. You sure it doesn't kick it out?
No, it
Okay,
just
excites it.
excites
Correct. Awesome. It excites it and it shoots it in same or opposite?
Different directions.
Alright,
same
perfect,
energy.
perfect. And then this can lead to a little bit of radioactive fog. Does anyone know what that is?
Say it again.
You need to know that.
Yeah, you need to know it. It happens to
And like,
us.
okay, foggy or something?
Yeah,
It's something similar to what?
So what causes the radiographic fog? It leaving or it coming in?
It's leaving. Because you know how it shoots it to a different direction? So that direction can end up on the IR from a different anatomy piece. So if I said, let's say I took an X-ray right here, it can shoot to a different direction and shoot down to that IR, which can cause not proper imaging, which leads to fog.
Because it travels?
Yeah, because it travels.
Where do you get the figure 10 kilovolt from? Write that figure.
How do you get 10?
What you said about it got the energy that was.
How do you get negative?
What was
100?
that energy from? 10 kilovolt?
It's just something you just have to know. You can't, there's no math equation for it or formula. It's just something that you have to know that goes with coherent or classical. Awesome. And then usually it often ends with a 20-degree direction. So if it hits here, it's a 20-degree angulation from the origin. And then fun fact, this is what Mr. Phung put, it also causes the color of the sky. So you know, you can use that and make it pretty smart during Thanksgiving, you know.
Why?
What is that?
Why? Also the cloud on the color of the sky. Why?
Right. So you know how like kids ask why is the sky blue? You can tell them, oh, it's because of coherent scattering.
Exactly.
It's not reflection of the sea, sir.
It's not reflection, it's not refraction, right? Those are lies your teachers told you. It is coherent scattering.
Really?
Within
Yes.
the atmosphere.
What is that?
It's radiation from an interaction with that, interacting with the atmosphere.
Right, so it's how light interact. So light is also photons, right? They're just lower energy photons than X-rays are. So it's how light photons interact with molecules in the air.
And that's the color of them interacting.
And that's how you get the color of the sky, yes.
Well, science.
You're so smart.
You just look things up.
Google.
All right.
Yeah.
So, our just want to follow up on Jalen's question. So right now it's just kind of memorization, but make sure you know scattering. Right, no matter what kind of scattering is involved in radiographic fog.
Radiographic
Fog.
Radiographic fog. Scattering leads to fog. It doesn't matter if it's coherent or incoherent. It doesn't matter if it's classical or Compton. Scattering leads to fog. In this case, coherent leads to a small amount of fog because you only have a small amount of coherent scattering. Okay, and Cody, why do we only have a small amount of coherent scattering?
Because it has to deal with like the amount of energy, right?
Mm-hmm.
Probably because there's not that many, I guess, low energy coming in to create so much of the radiographic fog.
Very good. So coherent scattering only causes a small amount of fog because we only have a small amount of coherent interactions. Why do we only have a small amount of coherent interactions? Because we only have a small amount of low energy photons. And Charo, why do we only have a small amount of low energy photons?
We only have a small amount of low energy photons because what is it, 10 or below keV.
Well, those are our low energy photons, but why do we have so few of them?
What do we do to get rid of? No. What do we do to get rid of low energy photons?
Oh, it comes out.
Filter it out.
Very good.
Everybody good on this slide? Everybody wrote it down? We're good, Charles?
I just opened the book.
Alright, awesome. So this one's my favorite. This is called the Compton scattering. So there's 3 names as well. So usually the way I like to remember everything that starts with an IN is usually Compton, and then the modified scattering. So it's just the reverse of what classical scattering was with the names. Does that make sense?
What was that side?
So you see how incoherent, so you go back, it's coherent, elastic, or modified Thompson. Everything is just reversed. That's the best way I can describe it to you. See, you see how it's incoherent and elastic? Instead of unmodified, it's modified. So it's just the complete opposite of the names. And so,
I also see Mickey.
huh?
Mickey.
Mickey.
M-I-C-I. Mickey. That's how I remember it.
Mickey.
Yeah.
That works too if you guys remember Mickey. Mickey
Good.
Mouse, Clubhouse. But the reason why Compton is my favorite, the difference between this and classical, instead of exciting the electron, it kicks it out this time because it now has 20 to 40 keV, so it has more energy to knock out that orbital electron. As you can see in the GIF right here, the incident X-ray photon interacts with the valence electron, as you can see, and it knocks it out. And it knocks it out into a 20-degree angle. You see it?
Yeah.
Okay, awesome. And so this can cause scattering. So this is responsible for most of the scattering. Small angle scattering, back scattering, and side scattering. Does anyone know what back scattering is or side scattering is by any chance? No? So it's just the different types of angles that it gives, that's the different types of scattering it is. For example, small angle scattering is what this is showing, right? It's creating a small angle scatter, right? But let's say backscattering. What do you think backscattering sounds like?
180 degrees.
It's going right back, 180 degrees back, right? So that's a key question. I see this on a lot of Mr. Phung tests. They might say, what type of scattering is backscattering? And it's 180 degrees, okay? Because it's going directly back. So, for example, instead of the secondary photon shooting this way, it will shoot directly back where it came from. And then side scattering, can you explain that? Is that with the body? Like, okay. So side scattering would just be going from north to south.
90
basically.
degrees over.
Right, more towards the 90-degree direction.
More 90 degree, exactly.
Doesn't have to be exactly, right? It's not exactly 180 or it's not exactly 90, but it's in that general direction, right? Small angle scatter, photon still going about in the same direction, still going kind of forwards, right? Side scatter, the photon is now going kind of sideways. Back scatter, the photon is now going kind of back the way it came. Doesn't have to be exact, just in the general direction. By the way, since we do have Aaliyah here,
Oh my gosh.
did any questions on backscatter pop up in your last exam?
Yes, I was so confused on that one. That had me stuck for like forever. I was like, no.
So, make sure you remember your small angle scatters, backscatters, and side scatters.
What is-
Backscattering is 180 degrees.
Approximately.
Approximately.
Yeah, I didn't know that.
Approximately.
What is small angle?
180 degrees.
Was I in the right direction?
Small angle.
That's
In the same direction, small angle?
Yeah, small angles like a little.
Like how many
you know,
degrees with that?
Instead of a straight line, it kind of angles off. So for example, you see my red marker?
Right, I'm like drawing this. That's why I was like, I'm so confused. I thought it was
What would small angle be like? 30 to 60?
20 degrees. Usually that's what they say. 20 degrees.
Do we have to be
Just going, talking about the direction.
No, I mean, and then,
So, no, you got it. Like, continue.
so for, it's usually 20. It was in the PowerPoint earlier.
Yeah, but that was for coherent scatter. So would it be 20 to like 30
No,
or?
it'd just be 20. Like roughly 20, you know. You just tell them the angulation, right? If it's 180, you know it's back scattering. So
Right.
if it's around 90 angle, side scattering, and it's just less than that, kind of side scattering to the side, right?
like, I didn't get this. This is zero.
Does that make sense?
I thought we were talking about this one. So it'd be like approximate 90 degrees scatter, you have one side scatter.
Yeah, kind of. If it's like 89, what would that be most likely close to? No.
Side.
Side, right?
Oh,
Side.
89.
89.
I heard 189.
Oh, no, 89. And if
That's
it
for
was,
side scattering, correct?
yeah, if it was 182 angle,
That would be for back scattering.
that's it. If it was 10 degree scattering,
It would be like, small angle scattering. right?
exactly, because it's
Yeah.
a small angle. 10
But I understand it, but when I get to a test, it's like, oh, what the heck is this?
Especially when he makes the test. So. Alright.
Yeah, when he makes the
One
test.
and only, Mr. Phung.
So everybody's good on this slide? Any questions? Everybody's good? Alright, on to the next. So Compton scattering interacts with middle or outer shell electron. It can knock it out. Remember, that's the key difference between classical. It can knock out the orbital electron. And with the energy, you know how in classical, when it hits the electron and it leaves with the same amount of energy. But with this one, it is absorbed with 1/3 energy. So highlight this, put a star next to it. This is very important. It leaves with 1/3 of the energy. Go ahead.
So does it leave with 1/3 of the energy?
No, it's
It
absorbed.
changes.
It's absorbed.
Right, so about 1/3 is absorbed, so how much does it leave?
It leaves with 2/3.
There we go.
2/3. Okay. It absorbs 1/3 and it leaves with 2/3 of the energy. And then the energy is higher than the binding energy of the electron, so that's the reason why the electron ejects from the atom, right? So the incident photon is lower energy than the electron in the orbital. What would happen?
It does not move.
Okay, and what's the name of that?
Possible
Okay, and then if the incident electron was higher, what would happen?
It kicks it out.
It kicks it out. Awesome.
It loses energy.
So just to make sure we understand this concept, if we have a 30 keV photon coming in and it knocks out one of those outer orbital electrons, one of those valence electrons, about how much energy would you expect the scattered or secondary photon to have?
The difference between
Probably
the
like
two.
20 something. 2/3 of 30.
Alright, so what's 2/3 of 30?
Whatever it is.
Something
Is
over
it
15.
20 is the 2/3 of 30.
I'm not a math
Okay, I hear
genius.
20,
Like 21.
What do you-
Wouldn't it be like 23?
23. Anyone else?
Say it again. What did you say?
So incoming incident photon has 30 keV energy, kicks out an electron, it leads with about how much energy?
13.
2/3 of 20.
Oh, 20.
So, what do you
Would it
guys
be like
think?
10?
10.
No.
2/3 of 30?
It's 20.
2/3 of 30, how much is that?
20.
20.
That is 20.
I know the numbers, come on.
Good.
It's 10, 10.
Oh,
Yeah, I was
Some people said 20. I
for
wanted
some
to
reason
hear
I was
more
thinking
people
it
say
was
20.
You weren't gonna
Oh.
Yes, you're correct.
Because if you divide by 3, then it's, each one is 10.
Correct.
So, 2 of them.
20.
Very good. That is correct.
Good job.
So notice that the number 1/3 actually pops up quite a bit, right? Well, I mean not quite a bit. It's popped up twice so far, right? Which isn't a lot, but it's weird that it happened twice. So we have. Where's the first time we saw 1/3?
The grams, right?
Grams.
Yeah.
That's right. Average energy of your grams. And now here's the second time you see 1/3, right? The amount of energy transferred to the electron. Okay, so just remember that number, 1/3.
So can you say Compton scattering is like associated with Brent?
No.
No.
Ah.
No, what does Brown and characteristic happen
In the anode?
inside it too?
Uh-huh,
And
okay.
all these interactions we're talking about
It's
happen outside
outside.
it too.
Oh, yeah.
Remember that.
So when do we get into radiation weighting factor?
Inside
Radiation weighting
outside.
factor? That will come when we talk about dose.
It's a phone.
So
Yes.
1/3 is absorbed.
1/3 is absorbed.
And what is 2/3?
That's how much energy the photon is left with,
The secondary photon.
Okay.
Secondary photon.
right? So remember how when we talked about energy, we used that like money example, right? So if I've got $30, right, I crash into the electron and the electron mugs me and steals 1/3 of my money. How much, right? How much did it run off with? It ran off with $10, right? So how much am I left with? 20, right? Same idea.
and some medical bills.
And some medical bills.
Mr. Mo,
And some
what is
trauma.
the exact-
Yes,
What's the
Charlie.
difference between Compton, what is the exact difference between Compton scattering and
Classical?
classical scattering? Try to make sure I'm on the right.
All right, great question. So let's figure out the differences. Okay, Reagan, what is our incident object that causes classical scattering? What is coming in to cause classical scattering? It's a photon. About how much energy?
Low, so like
Low.
10.
Good, great, under 10 keV, that's our incoming photon. All right, okay, Cody.
So is it anything below 10 or also equal to 10?
So, just you can think of it as 10 and below.
Okay.
It's not going to be that. It's not going to be that specific. It's,
Okay.
right? Under 10 or 10 and below. I mean,
So less
This-
than or equal to 10 kV.
it's really not much of a difference.
Classic, what we talking about? Classic.
Classical, yes,
Okay.
that's classical.
Okay.
Okay, Samantha, for Compton, our incoming item, what is it?
It is the photon?
It's a photon. Great. So it's also a photon, but how much energy does it have?
About, did we say it was like 20?
Right. So on average, it's going to be somewhere in the 20 to 40 range. Okay. So, right. So right, moderate, right? Moderate energy levels, right? So classical, low energy photon comes in. Compton, high, medium energy photon comes in. Great. Mansi, what does that incident photon interact with in classical?
An outer shell electron.
Outer shell electron, great. Sindhu, what does the incident photon interact with in Compton interactions?
Either outer shell or middle shell.
All right, outer to middle shell. Okay, great. So still kind of like on that outer part of the atom, right? So both of them are kind of dealing with the outer part of the atom. All right, Melanie, when that incident photon interacts with the orbital electron in classical scattering, what happens to that electron? So, photon comes in, interacts with the electron in classical, what happens to this electron?
Classical. In the classical
Changes
singing.
direction.
The electron.
In the classical singing.
It's excited.
It gets excited, right? It gets excited and starts vibrating. Very good. So does it leave the atom? No, it only gets excited. Great. Shamika, in Compton scattering, when that incident photon comes in and hits the electron, what happens to that electron?
It changes energy or direction.
So the electron specifically, what happens to the electron? The electron of the atom.
In Compton?
In Compton. So in classical, it got excited.
Yeah.
What about in Compton? Does it also get excited?
No.
Okay, what
It
happens?
strikes the outer and it knocks it out.
It knocks out the electron. So the electron leaves in Compton. It stays in classical, but it leaves in Compton, right? Okay, great. So, Angelica, in classical scattering, after the photon interacts with the electron, the photon leaves the atom. How much energy does that photon leave with?
It doesn't change the energy.
It doesn't change the energy, so it leaves with the same amount of energy it came in with, correct? Great. Okay, let's see. So Shaheen, in Compton scattering, when the photon leaves the atom, how much energy does it leave with? Good. 2/3 of the original energy. It lost energy. Right, so classical, no change in energy. Compton, we lose energy in our outgoing photon. Correct. The missing energy was absorbed by the electron. So, do you see the differences now between classical versus Compton? Okay? So, I recommend when you go home, do this exact same thing, right? Go back, make a little chart for yourself, and just go through every step, figure out what's the same, and figure out what's different. All right, but great question.
You
Ask questions like this on the test.
did better than
Yes.
us.
So 2/3 loses energy.
2/3 what?
Left.
Loses energy. Energy.
Energy. No, 2/3. It loses 1/3.
It's absorbed. 2/3 comes out.
1/3 lose.
2/3 comes out, but what is left? What is absorbed is 1/3.
1/3 is what is 2/3.
1/3 is absorbed, 2/3 comes out.
So secondary, you can say secondary.
Oh, Jesus.
Secondary photon equals 2/3 of energy.
Yeah.
Yeah.
It equals
So-
1/3 and you're left with
With 2/3, yes.
So the secondary photon has 2/3
The result is
left
2/3.
from the electron.
From
I mean,
the
from the
incident.
primary photon.
All right, so
Yeah, I'm lost
all right, so
now.
Shamika, please. So I'm gonna have you try and explain back to me what goes on with the energy.
I don't know.
Right? So,
Go ahead, try it.
from your understanding, from what
Okay.
you heard us talking about earlier,
Uh-huh.
photon comes in,
Yeah.
interacts with the electron.
Mm-hmm.
So two things are leaving the atom now.
Mm-hmm.
The electron is leaving, and the photon is leaving.
Okay.
So, how much energy is the photon leaving with?
2/3.
How much energy is the electron leaving with?
1/3.
Perfect.
Oh my God, that's how you.
I know. It's so difficult.
So that initial photon is the incident.
Alright, super down,
Yes.
super down.
photon.
I got you, girl.
Photon
Super
that's
down.
yes.
That was it?
That's leaving.
That was it.
Secondary
Okay.
photon, what's it called?
It's called secondary photon.
Secondary
Second
photon.
photon. It's there another name for secondary photon?
Right. So your secondary photon is also your scattered photon.
Scattered photon.
Or your
So the scattered
Compton.
photon means it's 2/3 of the energy.
Secondary scattered photon. And is there another name for incident photon?
Not the incident photon.
I just okay. Okay, awesome. And so we get into the really important part. Okay. So yeah, so the reason why Compton scattering is very important, this leads to increased patient dose, but it can interact with other atoms, which can lead to other interactions happening from there. And Mr. Phung, you get this one?
Yes. So what does that mean?
As in, which one?
So, right. So we have right now. What are we talking about here? Right, the electron. Right. So, photon came in. Two things come out. Right. One photon, one electron. Once again, how much energy does the photon leave with? 2/3. Great. How much does the electron leave with?
1/3.
1/3. That's what we said, right?
Yes.
All right. Now I'm going to tell you that that's not quite accurate.
Oh.
It was close. It was close. But how much it actually leaves with is based on this equation right here. So when it leaves, right, 1/3 of the energy went to the electron, but it needed some of that energy in order to leave the atom, right? Because there's the binding energy, right? You need to pay the toll. You have to pay the binding energy before you can leave the atom.
Oh, so you have
Right.
to.
So the 1/3 comes in, some of that 1/3 is used to pay the binding energy, and then the rest is how much it leaves with. So
That chart that you gave us last
Mhm.
semester with the binding energy,
Mhm.
that versus what it pays?
Correct. Right? So using the mugger example again, right? So I'm walking down here, right? I've got my 30 keV of energy, right? Jalen comes up, knocks me out. Boom. It takes 10 keV of energy, right? But why does he need that 10 keV of energy? Well, he's desperate, you see. He's got to pay his rent. Or no, he wants to move out, but there's like this down payment fee, or there's this contract, right, that he has to pay to get out of.
It's rough out here.
Yeah, it's rough, right? So he took the 10 keV of energy, and then he has to use some of it to pay the contract in order to leave his apartment. Right? So he's got his 10 keV, he's got his 1/3. He pays maybe 3 of it to the landowner in order to move out of the apartment. And so when he leaves, how much does he have left? He started with 10, he paid 3, so he has 7, right? So when he leaves, he's got some energy, but he doesn't have the full 1/3 anymore. That's because he had to pay the binding energy. He had to pay the cost of the binding energy. So photon comes in, two things leave. Photon leaves with about 2/3 of its energy. Electron leaves with 1/3 of the energy minus the binding energy. Okay, so that's the more accurate description of what happens.
Y'all's had that time. I remember this.
We don't need a break for this.
So please again, can you just say where does this photon actually comes in?
I guess I'll watch it.
What do you mean, where does it come
But
in?
now when you're saying when the photon comes in, and the electron leaves, and the photon leaves with 2/3 of the energy, electron leaves with 1/3.
Yes.
So where is this interaction taking place, and where
It is taking place inside the body. This
This X-ray thing coming in.
inside the body. Yes.
I see-
X-ray comes.
X-ray coming in.
Correct.
What happens inside the tube?
All right.
What happens inside the tube?
So, any questions about this top part right now? We're okay with what this equation is supposed to tell us? All right, great.
Okay, and so that scatter electron, it can also interact with other atoms. So the secondary photon can interact with other atoms, causing different types of effects, such as photoelectric and Compton. And then this is key. It's gonna ask what is the main cost of patient dose, and it's gonna be Compton scattering. Okay, so highlight that question or question right here.
Hold on.
That's different, right?
Correct. So this is not the main cause of patient dose, right? So right now, what we're talking about here is the electron. So photon comes in, two things leave. Photon leaves, electron leaves. When the electron leaves, where does the electron go? Well, it's gonna go only a short distance. And then after it travels the short distance, it's going to run into some other atoms inside the human body. Right? And when the electron hits some other atoms, it can do a bunch of different things, right? But generally speaking, it will slightly increase the patient dose. But because the electron is pretty much staying inside the body, it's not going to do anything for your image. It's not going to affect your image at all. So that electron will leave the atom, it will interact with other atoms, it will eventually get absorbed somewhere, right? It will very slightly increase patient dose, but it won't do much else. Okay? So it's not exceptionally harmful, right? Once again, this is specifically about the electron. Now, I think if you go to the next slide, the photon is a different story.
So, yeah. So, take a deep breath. So, Compton scattering. So, like you said, there's two. We have the incident photon and then the secondary photon. So, incident photon, that's what the X-ray beam is hitting. It hits the matter, and then it causes a secondary photon. So this is important. So this can cause a fog to the image, to the IR, and it can also lead to occupational exposure. So the way I like to think of Compton being like Compton from California. You know, it's really dangerous. You know, boys in the hood, right? We all
Yeah,
in there.
I always think about that.
Exactly. So it's very dangerous. So this is dangerous to us as occupational. And then Compton, since the range is from 2 to 40, just think of 30, because like Stephen Curry, you know, he's from Golden State, California. So that's the best way I can remember it. That might be reaching, but that's how I remember it. So yes, and so this is very key right here, okay? Right. So what causes the fog to the image again, Mr. Phung?
All right, let's see. Who do I want to act as Mr. Phung right now? Johns, yes. Okay, so Johns, what causes image fog?
So when photon leaves, or
when the photon leaves in a different direction, correct?
scattering leads to fog.
Scattering, that's right. So when a photon leaves in a different direction, that is called scattering, and scattering leads to fog. And Jay, what are the two types of scattering?
So far, Compton and coherent, or classical coherent.
Good. Compton and coherent, right? Other names for coherent, classical. Veronica, what is another name for coherent?
For coherent?
Mm-hmm. Coherent, classical.
Old name? Thomason, yeah.
Thompson. Great. Charo, another name?
You don't want to change your voice.
For coherence,
Coherent, yes.
is elastic scattering,
Okay.
unmodified.
Okay.
There you go.
All right. All right. Great. Very good.
You're gonna ask some questions where you instead of putting classical and coherent, you're gonna use
Yes.
other ones.
Best believe it.
Yes.
Best believe.
Okay, wait, I didn't put that in my notes. Wait, go back.
What was
And
Rayleigh
don't
again?
just study it and just think you're gonna remember it from then.
Rowley is also classical.
Always
That's
gonna
what I
be
thought.
here. We're not changing.
So yes, please do not expect all your questions to use the word Compton on it, right? Or don't expect all of them to use the word classical on it, right? Because sometimes you'll have a question that's like, all right, what kind of scattering takes place with photons in the 20 to 40 keV range? And your answer choices are going to be pair production, photodisintegration, photoelectric absorption, and instead of Compton, you'll see something like modified scattering.
Yeah, that's
And you're like, I don't see the answer choice here. Well, it's there, it's just under a different name. Okay, so,
Expect that.
yes, please expect that.
The only good thing is it's just Compton and classical that have the different names. So.
And then it's completely opposite from one or the other. So. Yeah, Jackie.
What are the differences between the, there's a
Electron and
circle,
photon
what's up?
between these two. Is that your question?
Not quite. So the above the line and below the line, there's two different circles.
That's just angulation of the.
Okay.
You know how we did backscatter, side scatter, and so what kind of scatter would this be?
Small angle.
Small angle, correct. Because going completely north and south, it would be what? side scatter, and just could go on completely where it originated from, that would be back scatter. Okay?
Yeah, I think that was east and west though.
Okay, gotcha.
And then backwards.
So yeah, so from this slide, this is the main part to take away, okay? That Compton scattering can hit the IR, the scatter, Compton scatter can hit the IR and cause image fog. And it can also hit occupational, like us, when we take the x-rays, okay? Everybody good on this? Any further questions?
Real quick, what do we call the radiation that reaches the IR? Remnant, very good.
Nice.
So for that first bullet point, can hit the IR to cause image fog. Would that type of Compton scattering be considered remnant?
Yes.
If it hit the IR, yes. Okay, what about the second bullet point? The scatter that hits personnel, that hits us and causes occupational exposure. Is that remnant? Not unless you're standing behind the IR, right? Right, so normally you're going to be standing somewhere else, bounces off the patient away from the IR to hit you. So not remnant, right? That is just scatter.
But we absorb it.
Right, we would absorb that scatter. And then that raises our dose, which we measure with our dosimeters.
And what is called when an x-ray from the tube and it hits the patient, what is that called? Primary. Alright, awesome.
Very good.
Very impressed. Alright, on to the next. So Compton scattering is not dependent on the atomic number and does not differentiate between soft tissue and bone. Unable to serve as a contrast medium mechanism.
Yes. It looks like you want to say something.
No, go ahead.
All right, so this is very important. Okay, this is very important. You need to know what is responsible for Compton scattering because the upcoming interaction is photoelectric and it has very different causes. One big difference is Compton is not affected by atomic number. You'll see later on that photoelectric is affected by atomic number. So make sure you are aware of that difference. Compton does not depend on atomic number. Photoelectric does depend on atomic number. What do we mean by this? What we mean is that you have fat, soft tissue, low atomic number, something like 7. You have bone, high atomic number, right? Something like 12 to 20. Normally, right, if you want to show the difference between soft tissue and bone, you would expect that bone shows up more white on your x-ray, fat shows up more dark on your x-ray, correct? Scatter does not differentiate between the two. Scatter acts the same regardless of if it hits bone or fat, soft tissue or bone. So there's no way for it to create a difference on your image. So it does not give you any anatomical information at all. Does that make sense? Because if scatter from bone and scatter from fat looks the same, there's no difference. You can't see anything. It gives you no information. Does that make sense?
Yes. Is that why, as you're saying, it's unable to serve as a contrast mechanism?
Correct. So contrast means differences. There's a contrast between bone and fat because bone looks white, fat looks gray. There's a contrast between bone and ear. Bone looks white, ear looks black. Right? There's contrast between fat and ear. Fat looks gray, ear looks black, right? Contrast means difference. You do not see any differences between these with Compton scattering. It treats them all the same. So you can't use it as a contrast mechanism. You can't use it to tell anatomy apart. So Compton scattering is useless for the purpose of creating a diagnostic image. In fact, Compton scattering is worse than useless. Compton scattering is actively harmful to your image. Okay, Compton scattering is harmful to your image. It destroys your image quality. So your goal should be to limit Compton scattering. How does it destroy your image? It's the F word. That's right. In radiography, the F word is fog. Right? You shoot an image and you're like, fog! I can't see anything, it's all gray. Fog!
Okay, that was your best one.
Right? In radiography, fog is your F word, and Compton scattering is responsible for the majority of your fog.
What does the fog look like? Is it just does it look blurry?
Yeah.
Correct. So imagine that you just, you know, like how you have Instagram filters? Imagine you had a filter that just made things look gray. Right? So suddenly it doesn't look black and white, it just looks gray, grayer, grayish. Right? So it destroys your image quality that way. You don't have as much contrast. You can't see the differences between things as much. All good?
I feel like we're so far along in technology though, they don't have anything that stops something.
So is there a way to reduce fog?
Not reduce, I mean like stop.
To stop. So this is all about physics, right? So
You don't have to go any further. If it gets too complicated,
the general idea is that no matter what technology we use, we are limited by physics, right? And what we'll find out, especially in this next section, is, go ahead, no, second bullet point, please. David, what do we see in that second bullet point here?
Higher energies increase ratio of Compton to photoelectric interactions. And what that means is that with that more higher energy, more chances of Compton occurring. So if you shoot, for example, if we take an image of the abdomen, right? There's a lot of tissue, there's a lot of things we have to penetrate. So we have to up the KVP, right? And so when we do the KVP, that means more Compton, which means more scattered, which means what? More fog, right? And so that's the reason why we have grids underneath to reduce the amount of scatter that's occurring.
So the thicker the body, the higher the KVP, the higher the Compton scatter.
Yes.
Yeah, so you can penetrate.
Yes, Cody.
When I was at outpatient yesterday, I forgot to ask about it, but there's like it's like a metal ball on like a stick.
Yes,
and
there
they, like,
is.
put it on the IR.
Yes, that is correct.
Absorb like the low stuff. Well, not absorb, but like.
So, Aliyah, can you explain it?
It's like ordinary, like, you're pointing at the joint.
Yeah, they said it was
They
for
need it for
measurement,
surgery,
just
right?
to like measure the volume.
Size reference.
It is for measurement.
The size reference.
Size reference, yes.
The size.
Very good. It is for size reference.
We've talked about this before.
I have.
Oh, yeah?
Yeah, you and I, like, I compared it, like, they do a coin to, like, an insect or something.
That's right.
Yeah.
We did talk.
They have one that's revolve and they're like, okay.
What do you mean by
LBJ?
You said measure? What do you mean by
Well,
measure?
to compare the patella and then that circle.
The circle is
They put it
constant.
right next to the patella.
It's always made the same, so.
Yeah.
It's like a little circle. Actually, it broke when I was there. So he used a
Well,
nickel.
why are
He
they
put tape on a
comparing?
nickel and he
Because
stuck it on the.
Why are they
He
comparing
said the
sizes?
surgeons want it just so they can compare, like, so they can know the size.
The size.
Oh,
Yeah.
okay.
Yeah, the
I was
size.
like, what's that
Yeah.
for?
But it broke when he used like a nickel with tape and then he just taped it on the
Okay, so
Interesting pills.
I thought I had a picture of it here in the book, but I don't see it yet. I'm still looking. But so that item that they're talking about, right? Not quite. So this has nothing to do with what we're talking about right now. Right, so just real quick side tangent. So you will see when you go to bone clinic that they will have a stand with a metal ball, and they use that. They put it right next to an anatomy that they want to know the size of. Right. So that ball is basically used for calibration. that ball has a known size, right? It's like 2 inches exactly, right? Because it's round, it doesn't matter which way you look at it, it's exactly like 2 inches or 1 inch across. In, right? In diameter, exactly. So, if you put that right next to the anatomy, it does not matter how much magnification there is of the anatomy. It doesn't matter what your SID or OID is. As long as you have the ball next to your anatomy, they can measure the size of the ball and then use that to figure out what the size of the patella is on the image. So, even if the patient had a bunch of OID, bunch of magnification, patella fills up the entire IR, right? Fills up the entire image. As long as the ball is right next to it, you can use that as calibration to figure out the size of all the anatomy in the image. And then we have digital tools on the computer as well to let us measure the size of items. And this is not the only time you will see this, right? Sometimes in OR, you might be asked to do something similar where they'll have like a screw and then they'll measure the screw and then they'll use that to figure out how long everything else should be. Yes, John.
So if the patella has OID, the ball would have OID too.
Correct. Correct. So the magnification for both would be the same, so they can still get the correct size. All right, but that has nothing to do with this. So let's get back to our content.
What made you ask that? What made you ask?
Because we were talking about like absorbing. I don't remember.
Okay, so let's see. Do we have another slide after this? Okay. So, all right. So let's just finish talking about this, and then I think we'll be able to head out a bit early. So, okay, content scattering. This is very important. Higher KVP, higher energy, increases the amount of scatter interactions. So as KVP goes up, your absorption goes down, your scatter goes up. You need to make sure to keep this in mind. Jalen used the example of the abdomen. The abdomen is a very, very good example of when this becomes super important. For example, let's say you've got a patient like myself, and they're like, all right, Mr. Phung, we're gonna do this X-ray 80 kVp 22 mass with grid. And it gives you a nice, perfect image. And then in comes a patient who is 2 or 3 times my size. And you're like, oh, all right. If I shoot my X-ray, I am not gonna have enough photons getting through to create a good image. I need to make a choice. Am I going to raise my KVP or am I going to raise my mass? Am I going to increase the penetration of my beam, my quality, or am I going to increase the number of photons, the quantity? What do you guys think we should do? Do I want to increase the quality, the penetrability of the beam, or increase the quantity, the number of photons that we shoot?
I think quantity.
Okay, if you had to only choose one.
Oh,
KVP? KVP?
Quantity.
Quantity, mass. Okay, so if you raise the KVP, yes, you will penetrate the abdomen more. However, what else will happen? More scatter. And because the abdomen is so much soft tissue, you're going to create a lot more scatter. You're going to create a lot more fog. So in reality, when you have a large patient like that, the first thing you should try to change is actually the mass. The mass will increase the number of photons. So hopefully, just by throwing more photons, you'll have more go through and you'll get your image. And by doing that, you're not going to be increasing your fog as much. So you're not going to get an increase in your content scattering. You're not going to cause fog. You're not going to gray out your image. Right? You're trying to keep that quality of the image the same. So the first thing you would want to do is change your mass. Now, of course, there comes a point when that is no longer sufficient and you will end up changing both. But even when you do that, keep in mind that you don't want to change the KVP first, right? KVP should not be your primary factor to change, just because it will increase the amount of scatter you have. Yes, Jay?
This might be off topic, but is this the sort of logic behind the transthoracic like view that we do?
The logic behind the transthoracic view. So
increase mass and like outside of orthostatic breathing, like it's not shot the same way as a normal like lateral chest.
Right. So, for example, with chest X-rays, right, just going between PA and lateral, right? PA, thin, right? Shooting through pretty thin, right? Lateral, thick, right? You're shooting through a lot of stuff. If you pay attention to your techniques on your PA and lateral, your KVP does not change. Just because you're shooting through more stuff on the lateral, the KVP does not change on your lateral. What changes? Only the mass, right? Only the mass. Why? 1, to maintain contrast. 2, to reduce scatter. Yes, Regan.
Okay, so I know like having to like retake images is bad and stuff like this.
Yes.
But like we're trying to like learn stuff in school, and
Yes.
like they said that you don't necessarily like learn how to like adjust mass and KVP. I know you're explaining it right now, but I know like different hospitals it's different. So like I don't know how to explain this to them.
Like, how do you get practice in?
Like just to see like what like it'll come out like, you know, because I mean it'll probably happen on accident to me anyways. Like I'll probably try and like take an X-ray and it, like the KVP or something like that be too low.
Well, at that point, I think it just becomes
probably
more of like,
charts and-
if you were like working, you know,
Yeah.
like if you think that image isn't good enough to send, and you think you know how to fix it, then I mean, if it was me, I would try and fix it.
I'm talking about now though. Like I want to see the difference now.
Oh,
like,
okay.
between,
All right. So something that you can try and do. Right. So number 1, you want to make a good relationship with your tech so that they trust you enough to start setting your own techniques, right? You want to show that you're paying attention to the techniques and that you know generally what to do, right? So at that point, you can ask your tech, hey, can I try making some small changes here and see if this still gives me a good image, right? So sometimes the text will be like, no, please just use my technique. And in that case, what you would do is, you do that text technique, copy down the session number, remember that image, you go to a different tech, a different rotation. They're like, oh no, I have my own technique for that, right? And you would be able to see the difference in techniques that way. Or if the tech does allow you to change things, then you can just see it right there between different patients. Like, I'll try one technique this patient, one technique that patient, one technique that patient. Okay. But of course, it all just depends on what your tech allows you to do. And once again, even if your tech doesn't allow you to change it, as you go between rotations, different techs use different techniques, so just compare between techs that way.
I know different machines is different too though.
That's true. That's true. So,
But that's something else.
yes. Well, here's how we are trying to all standardize to
Portable.
Philips, I believe.
Yeah.
Philips. So it should start being more even across the board. Yes, Jay.
So I was just gonna say like the numbers for like a chest would be KVP 85, mass 3.2, but going to the lateral it goes from at least a strawberry 120 to like 40.
All right, that's a great observation. So 85 kVp 3.2 for a chest X-ray. What kind of machine were you using?
This was trauma, so I assume it was either a portable or
I
Correct.
use 85 and
So if you use a portable X-ray machine, your KVPs and mass are going to be much lower. Why?
because there's no shielding around.
Not just that. What is your SID for a chest X-ray in the room?
72.
What is your SID for a chest X-ray portable?
Whatever they
Much closer, right?
Yeah, like 40, maybe 20.
What is that law? What is the law that describes the relationship between
Inverse square law.
inverse square law? What does it describe the relationship between?
Squarely double.
Distance and intensity. The number of X-rays reaching the IR, correct? So if our distance decreases, what happens to the intensity at the IR? Increases. To get an image, we want the intensity to be the same. So what do we need to do to our technique to drop the intensity? What do we need to do to our KVP or our mass to drop the quantity based on our emission spectrum? That's right, mass and KVP have to go down, so quantity goes down, so that peak goes down, right? See how we can kind of like start bringing all this stuff together? Right? So everything that you learned, right? Everything that you learned comes together in the end. You're not learning these separately, right? Please don't think of this as chapter 5 material, chapter 6 material, chapter 7 material. All of it comes together in the end. Okay? So all of it is related. Very good. All right. Jalen, any final things you would like to?
No, you guys are doing a really good job. You guys are pretty well knowledgeable about this pretty far. But one question, so what happens in the tube? What interactions happen in the tube? Okay, awesome. And then everything we're learning about this, where is this occurring? Okay, awesome. Well, that's it for class. That's it for me. Anything for you, Mr. Phung?
That's it. Have a great weekend.
Yes.
What happens? Yes, I'll release the grades now. I know.